helps us to understand the nature of the harmonic oscillators. Now, I am deriving an expression for which can be treated as a spring, a loaded spring, and therefore it is restoring the initial position of the particle, of any particle executing simple harmonic motion. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. All hitherto in this chapter, you have studied the concept of oscillations, enforcing my concentration on a specific topic called simple harmonic motion. We studied the three characteristics of SHM, where the first characteristic says simple harmonic motion is defined when a particle moves to and fro about its mean position. The second condition is that the acceleration of the particle should be directly proportional to displacement, and it has to be directed towards the mean position. We derived an expression for the velocity of a particle executing simple harmonic motion and acceleration, where velocity is maximum, where velocity is minimum, where acceleration is maximum, where acceleration is minimum. And we also studied the consequences of the simple harmonic motion. In my today's class, we will understand a very important law, what we call force law regarding simple harmonic motion. We will understand and derive an expression for potential energy, kinetic energy, and thereby total energy of a particle executing simple harmonic motion, and finally derive an expression for the time period of oscillations of a loaded spring. Therefore, in my first part of this session, we will understand a very clinical law, significant law, something called as force law. And this law also helps us to understand the vibrations of particles, oscillations of particles executing SHM, simple harmonic motion, as something called harmonic oscillators. Harmonic oscillators, in the sense particles which oscillate and exhibit simple harmonic motion. They are called harmonic oscillators, and the force law helps us to understand the nature of the harmonic oscillators. Now, dear students, referring back to the discussion on the acceleration of a particle executing simple harmonic motion. So the acceleration of a particle executing simple harmonic motion is given by A equals minus omega square into y. Derive madhudvi. A equals minus omega square y, where y was called the displacement of the particle from its mean position, and we derived an expression for displacement as y equals a sin omega t. A idana amplitude ant karadve, maximum displacement from the mean position. So students, acceleration of the particle executing simple harmonic motion, A equals minus omega square y. If you observe that expression, characteristic of SHM is established. Acceleration is directly proportional to displacement, and it is opposite to the restoring force. So, acceleration during any simple harmonic motion, A equals minus omega square y. Now, from Newton's second law, we have defined force as the product of mass into acceleration. So very clearly, I have done the derivation in that chapter. Force equals mass into acceleration. Now, what is acceleration? Minus omega square y. So, F equals m hage itkoltini. I substitute for A, which is minus omega square y. Now my intention is to group the constants on one side and the other terms on the other side. So force equals omega. Angular velocity is a constant. So omega square. Mass has to be a constant m. Take out y. So how I have modified or manipulated the expression, all constants I have brought to one bracket and the others separate. Omega, angular velocity, is a constant. M is a constant, and this is why. Therefore, F equals K into Y. If you observe that expression, K is replacing the terms within the bracket. K is a constant. It is replacing all the terms, or I can say all other constants in the bracket. Which are the constants? Minus omega square m, and this K is called as force constant. A very important term to understand simple harmonic motion. K equals minus omega square m, which is called force constant. And therefore, if you observe, the force is directed towards the mean position. Why do I say force is directed towards the mean position? Our force idiyalva, external force, adu mean position kadege direct agide. Why? The body has to come back to its original position, and therefore this force is called restoring force. See, a very beautiful word, restoring. Restoring andreno, it is bringing back the particle to its original position. It is restoring the initial position of the particle. So the characteristic of that force, the nature of that force is, it is directed towards the mean position so that the body regains its initial position, comes back to its initial position, and that is called restoring force. So this law is what is established as the force law of simple harmonic motion. Next one. Total energy of a particle executing simple harmonic motion. This is a very important 3-mark question to derive an expression for total energy of a particle which executes simple harmonic motion. ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ಟೋಟಲ್ ಎನರ್ಜಿ ಅಥವಾ ಟೋಟಲ್ ಮೆಕ್ಯಾನಿಕಲ್ ಎನರ್ಜಿ ಅಂದ್ರೆ ಏನು? Recall your law of conservation of energy, where I told total energy is nothing but the sum of kinetic energy and potential energy of a body. Very clearly I told, total energy is nothing but the sum of potential energy and kinetic energy of a body. That means, in order to calculate the total energy of a particle executing simple harmonic motion, first I need to calculate its kinetic energy, and then I need to calculate its potential energy, and that sum is called total energy. So first we start calculating the kinetic energy of a particle executing simple harmonic motion. Hagidre, what is the general expression for kinetic energy? It is half mv square. Very established. All throughout in mechanics we have defined. Kinetic energy is half mv square, where v is the velocity of the particle executing simple harmonic motion. Do I know the velocity of the particle executing SHM? Yes, sir. We have done in the previous session. Very good. It is A omega cos omega t whole square, because v square. Please refer back to that session. Go back to the definition of velocity. A omega cos omega t. But since it is velocity square, I have a whole square. Or it is half m a square omega square cos square omega t. You know, cos omega t whole square, a trigonometric term, is squared as cos square omega t. Now, the potential energy of a body executing simple harmonic motion. My dear students, I told any particle which exhibits simple harmonic motion is an harmonic oscillator, which can be treated as a spring, a loaded spring, and therefore the potential energy of a spring executing simple harmonic motion is half ky square, where k is a constant we studied before. It is called force constant, and y is the displacement of the spring from its mean position. Now, ಪ್ರತಿಯೊಂದು ಪಾರ್ಟಿಕಲ್ ನ ಇಲ್ಲಿ ಹಾರ್ಮೋನಿಕ್ ಆಸಿಲೇಟರ್ ಗಳನ್ನು ಟ್ರೀಟ್ ಮಾಡಿದ್ವಿ. Their oscillations is identical to that of a spring. So potential energy of a spring is half ky square. What was k? Omega square m. Just before I have done displacement a sin omega t whole square ಇದೆ. So again half omega square m. So this is a square sin square omega t. Therefore potential energy is half m omega square sin square omega t. So we have half omega square m a square sin square omega t. Now adding them together, if you observe the expression, I told total energy is nothing but kinetic energy plus potential energy. So I am adding those terms together. Observe Madi. Half m a square omega square is common on both expressions. ಆ ಎರಡೂ ಎಕ್ಸ್ಪ್ರೆಷನ್ಸ್ ಅಲ್ಲಿ half m a square omega square ಕಾಮನ್ ಆಗಿದೆ. What remains? Cos square omega t plus sin square omega t, which is 1. Therefore, I get the expression for total energy as half m a square omega square. And if you observe, m, mass of the particle is constant. Angular velocity is constant. So, total energy of any particle executing simple harmonic motion is directly proportional to the square of its amplitude. Very, very interesting fact. Problems are important. Shortcut for an entrance exam. Total energy of any particle executing simple harmonic motion is proportional to the square of its amplitude. Now, again a very important derivation where I derive an expression for the time period of oscillations of a loaded spring. My next derivation, I will derive an expression for time period of oscillations of a simple pendulum. But now I am deriving an expression for the period of oscillations of a loaded spring. So I'll consider a mass m which is attached to a spring of spring constant k. So this is the spring. I have attached a mass m to this spring and k is its spring constant. The restoring force, the force which brings the spring to its initial position, the force restoring back the initial position. See, as it is oscillating, it is losing potential energy. So in other term, restoring force will restore that lost potential energy. Therefore, the spring comes to its initial position. It is given by F equals minus Ky, where K is spring constant or force constant. Y is the displacement. From Newton's second law, again, force is mass into acceleration. I call them as equation 1 and 2. And dear students, can I equate equations 1 and 2? Certainly yes, because left hand side is force. So minus Ky equals m into A, or A is minus K divided by m into Y. I am just rearranging the terms so that I get acceleration. I know acceleration during simple harmonic motion. Derive madidini. Expression for acceleration during simple harmonic motion. A is minus omega square y. Now equate them. Y and y gets cancelled. Omega becomes equal to root of K by M. Omega square is K by M. So omega is root of K divided by M. We know omega is 2 pi f. What is the relationship between frequency and time period? Initial session I have told they are inversely related. Frequency is 1 by t, or t is 1 by f. So this omega is 2 pi, f is 1 divided by t. So 2 pi by t equals root k by m. I want the expression for t, which is 2 pi root m divided by k. So students, I have derived an expression for a particle, or you can say time period of oscillations of a loaded spring. So in today's class, we learnt a beautiful concept called force law, total energy of a particle executing simple harmonic motion, where total energy is proportional to amplitude square, and also time period of oscillations of a loaded spring. In my next class, we will study time period of oscillations of a pendulum and something called damped oscillations, resonance effect. Until then, have a nice time. Thank you.